Good morning, everyone. In the last class, we just started the metal clusters chapter. So, in continuation of that, we are going to have second lecture on metal clusters. So, in the last class, I have explained you. I have defined metal clusters, and in following of definition, classification is explained. Classification of metal clusters, and thereby classification of metal carbonyl clusters and in next I have explained you structures of trinuclear metal carbonyl clusters. Like that, I have explained you these topics in the last class. Now today I am going to explain you the structures of tetranuclear carbonyl clusters, and I am going to explain you the relative stability of bridged and non-bridged structures in trinuclear tetranuclear clusters. In tetranuclear metal carbonyl clusters. Right. So that is what today's class, and let's start the brief introduction of briefing of last class. Definition of metal clusters. I have defined the metal clusters as complexes with two or more metals in which direct metal to metal bonds and substantial bonds existing, right? Metal clusters are defined as complexes with two or more metal atoms having where the metal atoms has to have direct metal to metal bond and substantial bond, right? Substantial, it means having much more importance for the metal to metal bonds, right? How does the importance we have given is the structures of these metal clusters are depends upon the metal to metal bond rather than metal to ligand bonds, right? Before these metal clusters, we have seen multiple complexes where the complex structure is defined with respect of metal to ligand bonds. How does the metal to ligand bond as oriented? With that respect, we have defined the structures. Where it comes to metal clusters, it would be the structure would be defined with respect of metal to metal bonds in metal clusters, right? So that is what the substantial means, right? So next, where the metal clusters are classified into two types. Said that there are two types of metal clusters, right? And this classification depends upon the oxidation state of metal ion, metal in metal cluster, right? When there is a metal oxidation state is very much low, such as +1, 0, -1, like that, then thus metal clusters will be called as low valency metal clusters. And where the metal clusters having higher oxidation states such as +2, +3, +4, so on, and thus metal clusters will be called as high valency metal clusters, right? Where how does the low valency metal clusters and high valency metal clusters, low valency metal clusters, high valency metal clusters, where the low valency metal clusters will have oxidation state of metal oxidation states would be 0 or +1 or -1, right? Where it come to an high valence metal clusters, metal ion will have oxidation state from +2, +3, +4 and so on, right? And these low valence metal clusters also known as metal carbonyl clusters, metal carbonyl clusters, since most of the times the ligand will be carbonyl. Since the carbonyl is a neutral ligand, it never polarizes the metal ion to get higher oxidation states so far, and having strong ligand field nature, the carbonyl mostly forms an low valency metal clusters. So far, the most count from the low valency metal clusters getting by the metal carbonyl clusters. So these are all can also be considered as metal carbonyl clusters, right? Where it comes to high valence metal clusters will be called as metal halide clusters. Also, high valence metal clusters also called as metal halide clusters, since the ligand is halide. Such as chloride, fluoride, iodide, bromide, right? Such ligands can exist in the high valency metal clusters, where these ligands are negatively charged ligands. So as they are negatively charged ligands, they can polarize the metal ion into higher oxidation states. So far, the high valence metal clusters will consist ligand as halides, right? And when it comes to low valence metal clusters, these low valence metal clusters will be found or formed by the larger, or we can say that latter transitional metals will form low valency metal clusters, right? So we know that what it means by latter, what it means by earlier, right? When it comes to high valence metal clusters, they will be formed by the earlier transitional elements. Transitional metals will form high valency metal clusters. High valency metal clusters will be formed by the earlier transitional metals, which means first half of the D series will be found by the high valency metal clusters. The second half series metals in D block series. The second half series metals will be formed by the low valency metal clusters, right? And here the the bond lengths, bond order, when we see metal to metal bond order, here we will see most of the time it equal to 1. Bond order for the low valence metal clusters it equal to be 1 in most of the time. When it comes to an high valence metal clusters, the bond order of metal to metal bond order, it may be equal to 1 or less than 1. It may be equal or less than 1, right? Like that, the low valency metal clusters and high valency metal clusters are there. So in the chapter we are going to have the structural aspects of the low valency metal clusters and high valency metal clusters, and some of structural specific characteristic phenomena are we going to discuss. So let us start the first half of the chapter. That means it have the low valency metal clusters. In next we will have high valency metal clusters, structural relation and some of the features, right? Features phenomena. Let we start the low valence metal clusters. Low valence metal clusters will be most of the time they are metal carbonyl clusters. So we will going to have metal carbonyl clusters. Metal carbonyl clusters. And these metal carbonyl clusters, which are low valence metal clusters, are classified into two types, and the classification depends upon the number of metal atoms in metal carbonyl clusters, right? When the number of metal atoms are restricted till 4, right, then thus will be called as low nuclear metal carbonyl clusters, where number of metal atoms will be 2, 3, 4. 2 or 3 or 4, right? And there are second class which known as high nuclear metal carbonyl clusters, where the number of metal atoms will be 5 and more, 5 and more, right? So that's how the high nuclear, low nuclear metal carbonyl clusters. Nuclear metal carbonyl clusters will have sufficient number of metal to metal bonds. When it comes to high nuclear metal carbonyl clusters, the metal to metal bonds are deficient, will be have deficient number. So having sufficient number of metal to metal bonds in low nuclear metal carbonyl clusters, the low nuclear metal carbonyl clusters will obey 18 electron rule, and having deficiency in metal to metal bonds in high nuclear metal carbonyl cluster, the 18 electron rule not be obeyed by high nuclear metal carbonyl clusters, will not be obeyed 18 electron rule, right? So thus the metal carbonyl clusters are there. Now the structural aspects of trinuclear metal carbonyl clusters. Trinuclear metal carbonyl clusters. Here trinuclear metal carbonyl clusters will have the general formula of dodecacarbonyl trimetallic cluster, right? And here the metals which forms the trinuclear metal carbon clusters are iron, ruthenium, osmium. Iron group metal. Iron group metals will form trinuclear metal carbonyl clusters, right? Here see the structure. The structure will be in generally it have this structure where the metal to metal bonds are 3. In trigonally the structure will be formed, and each metal will carry 4 terminal carbonyl bonds. Where in case of iron, iron will have slightly different structure, where iron has same number of metal to metal bonds and structure will be trigonal, but when it comes to an metal to ligand bond, it has slight variation. The iron structure will have 2 bridged ligands. 2 bridged ligands it has. All these are trigonal structures, where the metal when it have ruthenium, osmium or mixed metals, it has structural features as 12 metal to carbonyl terminal bonds and 3 metal to metal bonds exist. When it comes to a metal with iron, this particular structure, in this case it has 10 metal to carbonyl, or we can say iron to carbonyl terminal bonds and 2 iron to carbonyl iron bridged bonds exist, and same with an 3 metal to metal, or we can say 3 iron to iron bonds will be there. So deviation comes for the ruthenium osmium structure to iron. Iron will have 2 bridged carbonyls and 10 terminal carbonyls, whereas ruthenium, osmium or mixed metal trinuclear metal cluster, all the ligands will be in terminal. Right? All 12 carbonyls will be in terminal. There is no bridged ligand, right? So having 3 bond in each, the structure will be unique. The structure will be same, such as trigonal structure. We will define as trigonal structure. To vary the structural aspects of ruthenium, osmium or mixed metal complex from the iron structure, we have to define the symmetry. To define the variation, we have to define the symmetry of these 2 structures. When it comes to ruthenium osmium or mixed metal trinuclear cluster, the structure will have the symmetry of D3H. Symmetry of D3H. When it comes to an iron trinuclear metal cluster, it will have C2V symmetry. It have C2V symmetry. The difference how we are defining this particular structure as D3H is this is have uniform trinuclear structure. It is uniform trinuclear structure. The vertex or the corner sides are one to other same. The corner sides are one to other same. All the corner metal having three terminal metal, four terminal metal to carbonyl bonds in all, right? So whereas here the iron structure will vary its structural aspect from structural will be slightly deviate where two sides are same but the other third one is vary from the two sides, right? The variation it comes by that the third side will have all four terminal iron to carbonyl bonds, whereas the two sides will have each three terminal iron to carbonyl bonds and two bridged carbonyl bonding. So that's how the variation, and this variation when we compare, this can be comparative with the water structure, or V shape, or it will be V shape. So when that is there, we know that water will be in the symmetry of will goes for the symmetry point group of C2V. C2V. Such how we have defined it, this iron trinuclear iron cluster structure as C2V point group structure. When it comes to the ruthenium osmium or mixed metal trinuclear metal cluster, it has uniform three corner sides. So this can be comparative with BX3 molecule. BX3 molecule where BX3 also having trinuclear trigonal structure where all sides of the corner sides will be same. X right here all sides will be MCO3 taken 4 times, right? So with that comparative, the BX3 we know that it is comes under into the point group of D3H. So that this particular structure we have defined it as D3H point group. So such slight variation we can explain for the trinuclear metal clusters from non-bridged structure to bridged structure, right? So when it comes to the 18 electron rule, as we said that low nuclear metal carbon clusters will obey 18 electron rule. Now count for the 18 electron count. When it count, it starts that number of metal atoms into the valency of metal atoms. Here all the iron group metal atoms will have 8 valency electrons, D6S2, right? So far it has 8 electrons plus the number of electrons donated by the ligand side. All here it is having carbonyl ligand side and it donates 2 electrons. So into 2 into how many ligand sides are there? There are 12 ligand sides. That 2 into 12 plus or minus oxidation state, it is 0. There is no oxidation state on the coordination sphere. So that is 0 plus the number of metal bonds into 2, right? The number of metal bonds are 3. 1, 2, 3. There are 3 metal to metal bonds, right? 3 into 2. Finally, 8 into 2 is 8 into 3 is 24 plus 2 into 12 is 24. 3 into 2 is 6. So altogether 54. 54. So 54 divided by 3 when we do, right, it will equal to 18 electrons, right? So it's saying that in each metal valency it have 18 electron density, nothing but it obeying the 18 electron rule, right? Having stability with respect of 18 electron rule, right? That's how the 18 electron rule in the trinuclear metal carbonyl clusters, right? So that's how the trinuclear metal carbonyl clusters. Now we have to go over tetranuclear metal carbonyl clusters. Till now we have discussed the last class. Now we are going to start today's session with structural aspects of tetranuclear metal carbonyl cluster. So here it comes, the structure of tetranuclear carbonyl cluster. General formula. General formula will be dodecacarbonyl tetrametallic cluster. Dodecacarbonyl tetrametallic cluster. The metals which will form the trinuclear metal carbonyl clusters will be cobalt group, cobalt, rhodium, iridium, cobalt, rhodium, iridium, which will be said as cobalt group metals. These will be forms tetranuclear metal carbonyl clusters. Right, coming to the general structure, they will form tetrahedral structure. Tetrahedral structure, where it will have, when it comes to an iridium, there are 4 iridiums on 4 sides of the tetrahedral, and each iridium will have bonded with 3 terminal carbonyls. 3 terminal carbonyls. And this iridium structure, when it compared with the cobalt rhodium structure, it has slightly varying, right? Such as iron varying from the in trinuclear metal carbonyl cluster, iron structure is varying from the ruthenium and osmium structure. Right here, the cobalt rhodium structures will be slightly in variation. The variation is just by the metal to ligand bond, but when it comes to the metal to metal bond, the structure is same, right? So far it is defined at the tetrahedral structure. Here all the metal clusters will define their structure with respect of metal to metal bond, right, rather than metal to ligand bond. When it comes here, one of the metal will have all 3 terminal carbonyls, where the other 3 metals will have each 2 terminal carbonyl bonds and each 2 bridged carbonyl bonds. Each 2 bridged carbonyl bonds. Like this. Like this, it would have the structure. In this both tetranuclear carbonyl cluster, it has 6 metal to metal bonds it has, and the geometry defined it as tetrahedral. And when it comes to an iridium complex, dodecacarbonyl tetrairidium complex cluster, it have all 12 iridium to carbonyl terminal bonding it has. When it comes to an dodecacarbonyl metal tetranuclear metal carbonyl cluster, where the metal may be cobalt, rhodium, or mixed metal. When we take there the metal to carbonyl bonds here will be two types. The 9 carbonyls will bound in terminal bonding mode, and the 3 carbonyls will bound in bridging mode. Right? So like this, the variation we can see in the tetranuclear metal carbonyl clusters. Now coming to the 8 electron count. 8 electron count is equal to number of metals, that's 4, into valency of metal, right? Here the valency of metal, they are all counts for the cobalt group, so they will consist D7s5 electronic configuration in valency. It means they have 9 electrons, so 4 into 9 plus number of ligand sites. Here number of ligands are 12 carbonyls so far. 12 in multiple with ligand donating electrons, that is carbonyl donates 2 each electrons, so for 2, 12 into 2 plus or minus oxidation state, plus or minus oxidation state, where the carbonyl, the tetranuclear dodecacarbonyl tetranuclear cluster will have 0 oxidation state in coordination sphere, so plus 0, plus number of metal to metal bonds, there are 6 metal to metal bonds are there, 1 2 3 4 5 6, both, right? 1 2 3 4 5 6, right? So having 6 metal to metal bonds, that is 6 into number of electrons in metal to metal bond, that is 2. So altogether 4 into 9 will be 36, plus 12 into 2 will be 24, plus 0 means 0, 6 into 2 is 12. So 36 plus 24 will be 60, 60 plus 12 will be 72. 72 number of electrons around all the 4 metal atoms, right? So when it comes to each metal valency electron density will be 72 by 4, that equal to 18. So that means the valency electron density count for each metal atom in the tetranuclear carbonyl cluster, it is 18. So it's saying that obeying the tetranuclear metal carbonyl cluster is obeying 18 electron rule, right? So this is what. Next, when we want to define the difference between these two structures, in tetranuclear metal carbonyl cluster, there are two types of structure, but the geometry is defined as tetrahedral for both. So to define the differentiation between these two, we have to define the symmetry. So when it comes to the iridium cluster symmetry, it is having an all 4 sides in tetrahedral structure are one and same. All 4 sides are same, all 4 vertices or all 4 corner sides are same. So far this particular structure can be comparative with methane. It comparative with methane. So we know that the methane will be have the symmetry point group of tetrahedral. So the iridium cluster will have tetrahedral symmetry. When it comes to other metal tetranuclear cluster, such as cobalt or rhodium or mixed metal cluster, will have 3 sides are same, the one side is different, where the one side having all 3 terminal carbonyls, whereas the other 3 metal sides will have each 2 terminal sides, each 2 bridged sides. So far these 3 will becomes in one type of vertices, corner sides, whereas here it is will be others, right? In tetrahedral structure, the first 3 sides, will be counts as same, but the fourth side will be different from the 3, right? So then this can be considered as chloroform. It can be considered in the form of chloroform, right? So where the three sides in tetrahedral of chloroform structure, three sides are same, the other hydrogen side is different. Three sides of chlorines are same, other side will be different. Whereas the chloroform has the symmetry point group of C3V. C3V. So like that, the point group variation will define the difference between the structural difference between the two types of structures of tetranuclear carbonyl cluster. And when we see the bond orders here, metal to metal bond order will be 1, right? Each between metal to metal bond order will be 1. So like this we can we can explain the tetranuclear metal carbonyl clusters geometry or structural aspects, right? So now next we have to go for relative stability. So when we see the tetranuclear or trinuclear metal carbonyl cluster, they are showing two types of structure. Some of the clusters are forming trinuclear bridged structures, some they are saying that non-bridged structure. So why the variation it taking place? When it comes to a trinuclear metal carbonyl cluster, iron is exhibiting bridged structure, and whereas the other ruthenium, osmium, or mixed metal trinuclear metal carbonyl clusters are showing non-bridged structure, exhibiting in a non-bridged structure. Whereas into the tetranuclear carbonyl cluster, iridium it exhibiting as an non-bridged structure, whereas the other metals, cobalt or rhodium or mixed metal tetranuclear carbonyl cluster are having a bridged structure. Why the variation is taking place? Where why they are exhibiting stables of bridged and some of are exhibiting as non-bridged structure in a stable form. So that the variation, that the difference we will be count or explain in terms of relative stability of relative stability of bridged and non-bridged structures of tri and tetra metal carbonyl cluster. Tetranuclear metal carbonyl clusters, right? Why some of the metals are exhibiting in a trinuclear bridged structure in stable form? Why some metals are exhibiting in non-bridged structure in a stable form? Stability, how they are gaining, why how that bridged structures are stable, how that the non-bridged structures are stable, we have to see in this particular title. So here the exact explanation or exact factors to define the stability of bridged or non-bridged is may not be having here, but the probability of factors we can explain in terms of two things. The probability of stability of bridged or non-bridged structures can be defined with respect of two factors. That is, one is steric hindrance, or we can say that steric factor, and the second thing is metal to metal bond length. With these two factors we can explain the stability of non-bridged and bridged structures in tetra or tri nuclear metal carbonyl clusters, right? So looking into a trinuclear metal carbonyl cluster, the iron has bridged structure. Dodecacarbonyl triiron cluster has bridged structure. Where the ruthenium osmium are mixed metal trinuclear metal carbonyl cluster will has non-bridged structure, which means all the 12 carbonyls will be in terminal mode. Terminal mode of bonding. Right. When we look into the sterical factor, when we explain the sterical factor here, the variation when we see here, the metal is iron. Here the metals are either ruthenium or osmium or mixed metal. When looking into these two, the size of the sites, here we can see that 3 parts of the molecule, right? This is the one, this is the second, this is the third part of the molecule. So when we look into the part of the molecule, right, when we replace iron by ruthenium or osmium, right, the size of the part is getting enlarged due to the size of the metal atom, right? From iron to ruthenium to osmium, the atomic size will be get enlarges, right? As it is, period is increasing, 3D to 4D, 4D to 5D. From iron to osmium, when we come, iron will be 3D metal ion, ruthenium will be 4D metal ion. When it comes to an osmium, it is in 5D metal ion, right? So what happens in group wise, top to bottom, the size will be get increases, right? So when the size of the metal atom is increasing, the difference we can see from here to here, only the metal, right? From the iron structure to non-iron structure, the difference we can see here, it is metal atom, right? As the metal, when we varying, the size of the moiety, right, part of the moiety will be getting enlarged, right? So as the size of the part of the moiety is getting enlarged, what happens? The one group to other group, the size enlarged groups, when they are coming to closer, right, what happens? There will be some sterical hindrance, it takes place, right? So large groups, when they come closer, they will have some sterical hindrance. Thus sterical hindrance make that to thus group to go one to other away, will be make has repulsion. Sterical hindrance will be creates, thus hindrance will make force to go two part of the group into one to other away, right? They will go away, right? So like that, here 3 groups, when they are the metal having rather than iron, when the metal it is having ruthenium or osmium, the molecule part will be become larger and larger, so that there will be create some sterical hindrance. There they will be go away one to other, right? They will be go away one to other, right? So in this case, the even the ligand side carbonyl can has 2 modes of bonding mode, right? It can be has terminal mode bonding mode, and it also has bridge bonding mode. The ligand carbonyl can behave as a terminal bonding ligand, and it can also behave in bridged bonding mode. Right? It can bind 2 or 3 metals also. With one carbonyl, it can be bind 2 metals or 3 metals. It has the capability of them. But when that is exist, when the metal atoms are getting closer, the carbonyl can be get bounded with 2 or 3 metals. Where here when we come in this particular tetrametallic dodecacarbonyl cluster, when it comes, as the metals are ruthenium or osmium, large size metal atoms, they will be go away from one to other. The groups of the molecule will be go one to away, one to other. They will be go away, right? They will be far away from one to other. Then when they go far away from one to other, the ligand side, carbonyl ligand side, cannot be reaches from one metal to other metal to have the bridging. To have the bridging, the carbonyl cannot be reaches from one metal to other metal. So when it is not reaching from one metal to other metal, it cannot be sure bridging bonding mode. Bridging bonding mode never be possible. So thus the mean the enlarged size or large size metal trinuclear clusters or tetranuclear cluster, as it is exhibiting spherical hindrance between one group to other group, one part of molecule to other part of molecule, there will be go one to other away. The part of the molecule go one to other away. So in this case, the carbonyl, even it has the capability of bridging, but as the metal sides are going one to other away, it cannot make any bridging. So far, the large metal sized, right, large size metal trinuclear or tetranuclear cannot be formed bridged structures. When it comes to an iron, it is a 3D metal atom. Size will be very very short when it compared with the ruthenium or osmium. So size when it getting very very small, right, the groups cannot be have any spherical hindrance, right? In small groups, when they come close, there will not be any spherical hindrance. So far, having no spherical hindrance, the one part of molecule to other part of molecule get closer, will be have get close into one to other. So having close interaction between one to other, the ligand side, whichever it is, then carbonyl, it can have the capability to reach from one metal to other metal. So thus make that the one of the carbonyl of one part of molecule to other part of molecule to have bridging. So far, the two carbonyls can have bridging in iron trinuclear metal carbonyl cluster, whereas in the tetranuclear metal carbonyl cluster also, when we see the tetra metal carbonyl cluster, it has the metals of cobalt and rhodium or mixed metals. So in this case, in tetranuclear metal carbonyl cluster also, the cobalt, rhodium are smaller size metal atom when it compared with the iridium cluster, dodecacarbonyl iridium. When it compared with dodecacarbonyl tetrairidium cluster, iridium is the fifth group, fifth D metal ion, right? Fifth D metal ion, where it 3D metal ion is cobalt, 4D metal ion is rhodium. So size when it compare, these are the smaller size metal atoms, whereas the iridium is larger size metal atom. So as the size of the iridium is getting enlarged, the sides of the four sides of the tetrahedral structure of this particular molecule will have spherical hindrance from one group to other group, one part of side to other part of side. There will be spherical hindrance will be created. There it will be go far away. There it will be goes far away from one group to other. So when the metal atoms are part of the molecules going away from one to other, the ligand carbonyl cannot be reaches to one metal to other metal. So it restricts to only on one metal. So far here all the carbonyls having in terminal bonding mode, there is no bridging sites. When it comes to rhodium or cobalt, the metal ions are very much shorter when compared to iridium. So there will be have no sterical hindrance from one part of group to other part of molecule. So one part of molecule to other part of molecule, there is no sterical hindrance, means they come closer. There will be have close interaction between one part of group to other part of group. So far, the three of the carbonyl sites in this tetracarbonyl, tetrametallic dodecacarbonyl cluster will make bridging, and thus bridging structure is stable for the cobalt or rhodium or mixed metals, where we can say that in this both we can say that the smaller size metal atoms, when they are forming in tetranuclear or trinuclear, they will be have exhibiting bridged ligand structures, whereas in the larger size metal atom, when they forming trinuclear or tetranuclear, there will be exist sterical hindrance. With the sterical hindrance, the ligand cannot be have any bridging sites. So far, they will exist non-bridging structures. Right? That's how the sterical effect we can explain. So when it comes then, second factor, metal to metal bond. Metal to metal bond lengths when it have. So in both, right, here I will take the tetranuclear carbonyl cluster. Structure of tetranuclear carbonyl cluster. When we take one of the side will have all three terminal, other three sides of metal atom has two to each terminal carbonyls and two each bridging carbonyls. Whereas the iridium structure is having a non-bridged structure, Iridium shows non-bridged structure or exhibit non-bridged structure, where all the four iridiums will have three each terminal carbonyl bonds. So the difference now we will count with respect of bond lengths, right? Again, the size of the metal atom will count here, right? So when there is a metal is cobalt or rhodium, the size of the atoms will be very very small when it compared with the iridium, right? So having smaller atoms, cobalt or rhodium, the length between two atoms will be less, right? Metal to metal bond length will be less, whereas in here metal to metal bond length will be large. Right? So when there is a metal to metal bond length is very much shorter or smaller, then what happens? The one of the group of or one of the part of carbonyl can reaches to the other part of the metal atom. One metal atom's carbonyl can reaches to the other metal atom when there is a length of the bond when it is lesser and lesser. So having lesser bond length, the carbonyls can reaches from one metal to other metal. There it will having a bridge structure. Possibility of bridging structure is there. When there is a metal to metal bond length is very much larger, right? When there is a bond length from one to other metal atoms is larger bond length, the one of the carbonyl or one of the iridium cannot be reaches to the other iridium. So to have the bridging bonding side, so the carbonyl can restrict in the one metal atom only, and it is exhibiting in terminal bonding only. So due to the bond lengths also exhibiting larger bond lengths will be supposed to have non-rigid structures. When there is a bond length shorter, there it supports for the or uh, gives an possibility of the bridge structure. So far, the carbonyl, cobalt or ruthenium will exhibit the bridge structures in tetranuclear, whereas in trinuclear metal, iron to iron bond lengths also very much shorter when it compared with the ruthenium osmium bond lengths in the trinuclear. So far, the ruthenium osmium bond lengths as it is existing larger bond lengths, the carbonyl cannot reaches from the one ruthenium to other ruthenium or one osmium to other osmium. There will not be any bridged structure, bridged bonding. So far, these trinuclear clusters of ruthenium osmium will have non-bridge structures such as iridium. And when it comes to iron having lesser bond lengths from one to other, right, the closer interaction will be there between one part of iron molecule to other part of iron molecule. So far, there will be bridging is possible, right? The bridging is possible. So far, these particular structures will exhibit the bridging structures, right? So having lesser smaller size metal atoms will having lesser bond lengths, no spherical hindrance, will exhibit bridged stable structures, whereas in the large metal ions having spherical hindrance and larger bond lengths, there will be have non-bridge structures in a stable form, exhibit in the form of non-bridge structures, right? Like that, there will be relative stability. We can compare between bridged structures to non-bridged structures in trinuclear and tetranuclear metal carbonate clusters, right? Here I will stop. By next class we will continue the other topics. Thank you.